Well, hello there, ap1. I hope you're all still out there and had a nice Easter break. A break from what? I'm not sure, but there we have it. Anyways, today we are going to finish chapter 14. We're going to be doing the third video part, and this video is on a process called the Doppler effect. Woohoo! All right, Doppler effect, page 468. Well, technically the bottom of 467, but page 468. The Doppler effect, well, basically, the way that you perceive a sound depends on the relative motion between you, the observer, and whatever that source of sound is. If the source of sound is a speaker playing music, or the source of sound is an ambulance blaring its siren, and you and your ear are the detector, okay? Well, if there's motion between you and the source of sound, the frequency that you observe will change. Right? Sound is produced by the source at some frequency. Remember, frequency is the rate at which, as the number of cycles per second. So you can think of the frequency of sound as the rate at which the wave crests hit your eardrums. So middle C is 256 hertz. That means that middle C, the wave crests from that sound will strike your eardrum 256 times every second. Any sound that has that frequency is middle C, okay? Now, if you're moving towards the source of sound, that means the sound is coming at you 256 times a second, but as you move towards the source, you're going to be receiving those sound waves more frequently because you're moving towards it. And because you're going to receive those sound waves more frequently, you will hear those sounds at a higher frequency. By the way, higher frequency would mean higher pitch, more treble. If you're moving away from the source, the sound waves will arrive at your ears less frequently, which means you would hear it as a lower frequency. Lower frequency would mean lower pitch, so bass. Okay? So we got treble and bass, high frequency and low frequency, based on the motion between the observer and the source. Let's see if we can make some sense out of this. Let's try a video. In this little video, and you know why I love it just looking at the animation already, the red thing is going to be our source, the green thing is the detector. So let's hit play, and the red thing starts making sound waves. Those yellow circles are the sound waves. Imagine you're looking at the sound wave from the top, and the yellow circle is the crest of the wave, and in between yellow circles is going to be the trough of the wave. So whenever a yellow circle gets to the green guy, that is the top of the wave, that is the crest of the wave reaching the eardrum. And you'll notice if you look at the green guy that the waves are going to arrive at him at some frequency, right? So, ding, 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 ding. Now, trying to pause this. Okay, you'll notice, he already started it, but you'll notice when the green guy starts moving towards the red guy, the waves are going to arrive much more frequently. I'm going to rewind this a hair and see if I can make this work. All right, okay? So the green guy, ting, ting. Now he's moving towards ting, 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 ting. Notice the frequency got much higher, okay? Trying to pause this. I'm going to rewind it. Notice when the green guy moves away from the red guy, the frequency is going to be much slower, okay? Ting, 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 ting. So the frequency that was heard was dependent on whether or not there was motion between the green guy and the red guy, motion between the observer and the source. When there was no motion, you had the regular emitted frequency. When the green guy was moving towards the source, the frequency went up. He arrived at those waves faster. When he was moving away from the red guy, when he was moving away from the source, the frequency of waves was decreased. It took longer for each wave crest to get to the person. Okay, so that increase and decrease in frequency based on the relative motion is called the Doppler effect. And you've heard it before. So let's do some math. Oh, before I do math, on page 468, case 1, below that, case 2, on the next page, the general case, this is all done very poorly in my mind. I do not like the way the book handles this, so I'm going to show you a much better way to think about this. So we're going away from the book slightly. So Doppler, oops, and mathematics. Let's go. Come on, why can't that erase? Okay. So, dang it. Erase. scroll. Now right. Okay, here we go. Mathematics. We're going to need to have a detector and a source. So let's try this. There is our detector. There is our source, and the source starts making sound waves. The sound is traveling in that direction, and I'm going to use v for the velocity of sound. V is the velocity of sound, okay? I know you should think it should have a subscript, but in this case, we're not going to do that. V is the velocity of sound. Sound always goes from the source towards the detector, okay? So, if there's no motion between the two, we'll get some observed frequency. If there is motion between the two, that frequency changes. How is that frequency going to change? Well, let's use this equation. The frequency heard by the detector is equal to the frequency emitted by the source. Remember, subscript D means detector, S means source. S does not mean sound, S means source. Detector, source. So equals the frequency of the detector times the quantity. V, that's the velocity of sound, minus the velocity of the detector, all over the velocity of sound minus the velocity of the source. Remember, that's the source, that's the source, that one is sound. Okay? Okay. Let's get this out of the way. All right, so there's our equation. Now, v, the velocity of sound, to use this equation, and how this is going to differ from the book, is the following. We have to use this equation will always work. You do not need a different equation for different circumstances. This equation always works, provided we use a coordinate system where sound is the positive direction. Sound has to be the positive direction. So in my example, the positive direction is to the left, okay? We could draw that the other way if we wanted to. We could do it like this. You could have the source over here, and you could have the detector over here. The source makes sound, and that sound is traveling that way towards the detector, okay? And we're going to call that the positive direction in that example. So in that diagram, sound is traveling to the right. The right is the positive direction. In this diagram, sound is traveling to the left. To the left is the positive direction. It doesn't matter how you draw it. Sound goes in the positive direction. All right, the detector. Let's see here. The velocity of the detector could be 0, no biggie. The velocity of the detector could be that way. The velocity of the detector could be that way. In this coordinate system, that velocity right here would be negative. That one would be the positive one. The source. The source could have a velocity of 0. The source could be going that way. The source could be going that way. In our coordinate system, that would be positive. That one would be negative. Okay? In our other silly coordinate system, the source here, that would be the positive direction, that would be the negative direction, because velocity has to be positive. For the detector, that would be the positive direction, that would be the negative direction. The source, the positive direction is the direction of sound. Okay? Now, how do we use our equation? Well, the frequency heard is going to be the frequency of the source times this quantity, the velocity of sound, and then minus the velocity of the detector. The problem will tell you if the detector is moving towards or away from the source. In this example, if the detector is moving towards the source, we would have the case of the negative velocity. So you'd be minusing a negative number. Let's do a problem with some let's actually do a problem and we'll illustrate all this. So let's do on page 470. Let's do problem 14.4. This says, listen, but don't stand on the track. So we got a train moving at a speed of 40 meters per second sounds its whistle. Okay, so the train is the source of sound. So the velocity, we'll draw a picture here in a second. I'm going to get some numbers here. The velocity of the source is 40 meters per second, okay? And its frequency is 500 hertz. So the frequency of the source is 500 hertz, okay? Back to the problem. Determine the frequency heard by a stationary observer, Okay. So the velocity of the detector, the observer, is stationary. Okay. As the train approaches, the temperature is 24 degrees. All right, so the reason they told us the temperature is 24 degrees is because we need to figure out what the velocity of sound actually is, right? We need to know what this is. And the temperature, they said, was 24 degrees. All right, so we're going to use our fancy equation, and let me see how I scroll here. Let's scroll. So the equation we want to use. The frequency heard by the detector is the frequency emitted by the source, velocity of sound, velocity of detector, velocity of sound, velocity of source. All right, the velocity of sound. Well, let's see. We don't know that right now. We're going to need to look up an equation for that because they told us that 24 degrees thing. If you're not told anything about the velocity of sound, 343 meters per second is just perfect for it. Where's my book? There's my book. Okay. So notice right here they use an equation. Use equation 14.4. Velocity is this to calculate what the speed of sound is at 24 degrees. And you'll notice they came up with 345 meters per second. Okay? So velocity is 345 meters per second at that temperature. So we want to calculate the frequency heard by the detector. So the frequency heard by the detector is going to be the frequency of the source, which is 500, times the velocity of sound, 345, minus the velocity of the detector, which we were told was 0, over the speed of sound, 345, minus the velocity of the source. Well, what direction is the source traveling? The train is moving at 40 meters per second towards the station. The observer is at the station, so the source is moving towards the observer, right? So what is that going to look like? Well, let's go find a picture here. So we've got, in that case, we've got the source is moving like this. Here is the detector. So the sound is going to be going this way. The source has a positive value because the velocity is positive. So the source is going to be a positive velocity. So we're subtracting a positive 40 meters per second. And that would give us a frequency equal to, if we did this right, 566 hertz. 566 hertz. Well, I hope that mess makes a little bit of sense to you guys. At this point, I have now been through problem 14.4. So I did example 14.4. You guys should now work on exercise 14.4 and play around with 14.5, the exercise and the example. That is going to conclude, to the best of my guesses, what we need to do for Chapter 14. So at this point, also start working on your Chapter 14 homework, and we'll talk soon about how we're going to deal with the test. At any rate, over and